Hello everybody, so I'm glad to be here with the ABC community to talk about our work with Abyss NGO at La Réunion. Acoustics is primary for dolphin and many behaviors can be observed with acoustic production. But only 1 to 10% of the total activity appears at the surface. So to study underwater behaviors, it seems natural to use both passive acoustic array and video. So based on that idea, we developed Stethoscope, which is able to record the visual scene and its associated soundscape. The device is not so expensive, it is robust and easy to deploy. It is made by a tubular stainless steel frame on which the user gonna clip 4 poles equipped with hydrophones. At the center, the digital recorder, the 360 video camera and batteries. And the shape looks like a tetrahedron. The software is made by 3 independent parts coded in MATLAB. The first is the acoustic detector dedicated to signal processing and the extraction of times of arrival. Second is the 3D sources localization algorithm. The representation can be static or dynamical, like a movie. Those 2 parts are already done now and operational. The third is the fusion of the acoustic position with the video, and it has to be done in control environment. It is in progress now. About the localization, the previous method was based on hyperboloid intersection, but results show a lot of ambiguity and it was very time consuming. So our new approach take advantage that the space we want to localize is pretty small. So we can compute the theoretical TDO as before, and then new observed data just have to be compared with this theoretical grid. So we did some simulation, 10,000 points have been simulated. We can compute the error between the estimates and the real position. So we get 0.8 meters in average and 1.2 for the STD. It was interesting to see how looks like the error in 3D and not only in the mean values. We can see a shadow area linked to the shape of the array, and it change with the relative depth of the sound source regarding the array. So now let's have a look on real situations.
In this first video, a single dolphin is approaching and clicking at the same time. On the background, the video scene, on the right, acoustic positions, and at the bottom, the scrolling spectrogram. We can see and hear when it starts clicking. We have the positions, we have the arrow is going slowly at the surface. With this second video, we're gonna check that it works also on whistles. The dolphin is going to pass in front of the camera. He's going fast and is emitting whistles at the same time. And right on the top of the graph representation, you have just seen some clicks emitted by other individuals. In this last recording, the situation is a little bit more complicated as several dolphins are approaching Stethoscope and turning around. But we are able to differentiate which one is emitting and what is their specific behaviors.
Okay, it's time to conclude. So this work have shown encouraging outlooks. Stethoscope was easy to deploy and robust. After many deployments, it's still in good condition. Combining video and passive acoustics observation was helpful to identify the behavioral context of the sound production, and we can imagine a new application like identifying individual vocal signature or measuring acoustic source density, noise of bioacoustics. Further improvement have to be conducted, optimizing the time of computation, calibrating the video camera and the acoustic localization, so the visual rendering will be higher and the analysis easier. studying the localization abilities related to the size of the array. What happened for bigger animals like baleen whales, and what about low frequency sound? Thank you for your attention.